So one can make a combination of transistors that acts like a transistor itself, but will have a much larger gain. And we do that by basically cascading one transistor into another, and we call these Darlington configurations. And if we have two transistors, the gain of the combination is just the product of the gains of the individual one. We can either use two NPNs like this, where we take the emitter of the first one and put it into the base of the second one, so that we have a gain here, and that gain gets multiplied again in the second one. We can do it with two PNP in the same way. In this case, the drop between the emitter and base, or the base and the emitter in the NPN case, is twice the normal diode drop, so like 1.4 volts. We can also combine a PNP with an NPN, or the other way around, and now we'll only have a single diode drop between the two. We still take the product of the two gains. One has to be careful that the first transistor, where the actual overall base goes into, has a large enough gain, even at low values of IC, for that part of the transistor. You may have noticed, well, we often talk about the base emitter junction being a diode. We can make this more explicit if we connect the collector to the base itself. Now we actually just have a diode. In other words, when we make sure that VCE is 0 by connecting the two with a short circuit, we have a diode. In this case, if the VB, the base emitter voltage, is greater than 0, a current will flow actually greater than a diode drop. It actually just works like a diode. Most of the current does flow through the collector, however. So we can use this basic design to talk about the current mirror. In a current mirror, we use one transistor to control the current in another. Now, for a current mirror to work, we have to have identical transistors, which I've told you is not usually the case if you take two separate transistors, even if they're the same model. However, you can make two transistors on one piece of silicon, in which case they will have nearly identical properties. So the idea is that we control a current by connecting a power source through a resistor, through a transistor going to ground, and we can control the size of this current by the resistance. And we know that we'll have a 0.7 volt drop across this way, so we know exactly how much current will flow. So in particular, VCC over R gives the current. Some of that goes through IB and some of that goes through IC. Now, since the two transistors are identical, this current that flows through IB will go both ways, an equal amount in both ways, in fact. So IB, little IB, as I've called it here, which is the current into either of the bases of the transistors, this current on this path, capital IB, will just be double that. So either way it can go, it will be identical way to go to ground for each. And so the current that goes through IC, little IC here, will be the same as the current I out coming in this way. And that's just going to be beta times IB, right? So when we do the calculation then, the input current gets split into IC and 2 times IB, which is capital IB. And that equals these two base currents plus beta from this side. And then we can solve for IB from this, and we find that it's the input current divided by 2 plus beta. And the output current is beta times that. And when we factor that out, we'll have a factor beta over 2 plus beta. And as beta goes to a large number, basically the output current will be the same as the input current that we can control. You see there's just this little factor of plus 2 beta there. We can actually reduce that even further by putting another transistor in the sequence. And the same part works here, but now we've taken off even less current because we've separated off a small amount here, but the main part of that base current comes from Q3. That ends up giving us a beta squared, essentially, rather than just a beta. So in this case, we have even closer to a direct current mirror. Another common transistor circuit is called the push-pull circuit, and the idea for it comes from the emitter-follower. The problem with a normal, just a normal emitter-follower, remember the gain is nearly 1, is that you have to bias it positive. So that V in here has to be biased so that this is positive so that V out is greater than 0. If the input here goes lower than 0, then the transistor turns off, and that makes it less useful. We can fix this by having two transistors, one NPN, one PNP, and then going between symmetric voltage supplies so that this one works when you're below ground and this one works when you're above ground, or above 0 voltage here, then we flow, and this one's on below voltage here. In each case, V in and V out form a voltage follower, but it works in both cases because one transistor or the other will be on. Now we can analyze this in detail by making a small signal model of this. So in our small signal model, we'll replace each of the transistors with our normal gain model, and I'm going to explicitly keep, this is not the small signal model, just the beta model, where I put a diode on the emitter of the appropriate direction. And so we see that if the voltage is positive, then I can get current to flow this way, and then I will pull out the current here as well, and then V out will be on. But that only works if V in is greater than the diode drop here, or 0.7 volts. In that case, D1 will be on, D2 will be off because it's quite reverse biased here. When V in is negative, below minus 0.7, then this one is forward biased. It will come this way, we'll get a current to flow, and V out will just be this diode drop below V in. In that case, D2 is on, D1 is off. However, there's dead space in the middle, where if V in is between minus 0.7 and plus 0.7, both diodes will be off and V out will be 0. So if we have a sinusoidal signal coming in, we'll get a output that has dead space in the middle, and we call that crossover distortion. The signal will look like this in that case. You have the top half of the signal, the bottom half of the signal. The input looks like this. The output looks like what I drew the first time, and the fact that those are different is a distortion called crossover distortion. We can fix crossover distortion by adding an extra diode here to take care of the diode drop there. So a final transistor circuit that we'll consider is called the differential pair. In this we have two pairs of transistors. They should be identical as in the current mirror, and it makes a very fine amplifier. It amplifies the difference in voltage between V1 and V2, which should remind you of the op-amp. In this situation, the amplification comes from before. We're looking at the voltage at the collector of these circuits. And notice that I have a current source here which biases these transistors to be to have some current flowing through. I'm pulling the current through. That's what does the bias. So we can analyze this using the small signal model. Basically, we want to use the KVL So imagine there's a voltage source here and here. We're going to do KVL along this path. We replace each of the transistors with its small signal model, so it has an input resistance on the base. We have the gain from the collector, and then we have just the emitters connected here to the current supply. But remember, the current supply in the small signal model is going to be I equals 0. And the gain comes from the collectors, and remember, we're looking at between the collector and the collector resistor. So if we do a KVL loop along here, we have V1 minus IB1R1 plus, because we're going backwards, IB2R2, and then minus V2 back down to 0. And because we have identical transistors and we've biased it with some current, R1 equals R2, and they're both VT over IB. And IB is going to be replaced with I0 over 2, that's what's flowing through here, divided by beta to go from I0 to IB. And so we have that the current IE1 equals minus IE2, and that IB1 is minus IB2. So now I can calculate what's the difference between V1 and V2. And so I plug in, well, that's just this and that, the difference of those two. The resistances are the same, so it's just the difference of the currents. So the difference of the voltage is proportional to the difference of the currents. The minus sign, the order is different. And I plug in what those are. So that's, well, they're the same magnitude but opposite sign. So I plug in for the gain 2 beta VT over I naught. That comes from here and what the resistors are. And then the difference of the currents, because they have the same magnitude, different sign, just gives us another factor of 2. So putting that all together, when we analyze the small signal model, the voltage difference will lead to a current flowing on the two, and that current will be of this size. Now, we need to find the differential, the gain, and get the output, so V out 2 will be proportional to IB2 that we found is proportional to the difference of the voltages. And so if that current just comes up here, it's easy to calculate what this voltage is. So that's just IC2, which is beta IB2, times the value of that resistor. So the gain in the end is just going to be the current that we draw through times this resistance divided by the thermal voltage and a 4 that we got from the various factors of 2 and the difference in voltage. So the gain is proportional to the difference of V1 and V2 times this factor of RC2 over 2R pi, or I naught RC2 for VT. So if we change V1 and V2 together in this model, there won't be any gain at all, so V out 1 or 2 will not change if we change V1 and V2 together. However, if we replace this with a resistor, then there will be some what's called common mode gain.